Well, good evening, everyone. In this experiment, I want to quickly show how power factor can be corrected using static capacitor to compensate for the lagging power factor. Like we have already known, power factor lagging happens due to the presence of inductive load. When your load is inductive, it tends to draw excess reactive current from the system. That is, not all the power that is generated is used by the resistor or is used to carry out the actual work or the actual load in the system. Some of those currents are used are stored or are consumed by the coil of the inductor. For example of inductive load are all these induction motors. Transformer is an inductive load, inductive motor, all these heavy equipment that have large coils. That is why industrial premises that have heavy machineries are always overtaxed, because most of their load consume what we call reactive load. So if you check your laboratory, if you check the laboratory manual we are using, you see that the essence of this laboratory tool is to actually do power factor correction. Now this triangle that you are seeing on your page is what we call power triangle. That is, it considers the ratio of the three powers that we have in electrical engineering, that is the active power, reactive power, and the apparent power. The active power is the actual power that is consumed by the resistor, and that is the power that is used to overcome, that is to carry out an activity. While the reactive power is the power consumed by both capacitor and inductor. Then the apparent power is the summation, the vector sum of the two power mentioned earlier on. So the whole essence of power factor correction is to make sure that the reactive power is reduced to the barest minimum. And when the reactive power is reduced, right from what you can see on the board, you see that the essence is we are trying to invariably reduce the phase angle between the voltage and current, that is the phase angle of the system. Remember, when you have 0 degree as the phase angle between the voltage and current, that means the power factor becomes 1. Just like in the case of resistive load that we did the other time, when the power factor is given as 1. So when you improving power factor, you are reducing the kVAR and you are reducing the phase angle that separates the two of them. So without wasting much time, let's quickly launch our simulation tool, that is LT Spice. So I've patched up this simple circuit. You can simply connect this circuit. It's easy to connect. Let me maximize it for everyone to see. This is just voltage source, resistor, and inductor. Now the inductor, we assign a value. It's just an experimental value. The essence of this lab, we are not going to actually record anything. It's just for us to see how power factor correction takes place. I've assigned a value of 4 Henry. Then the resistor, I've assigned a value of 100 ohms. Then this the power supply, I've assigned a value of 5 volt amplitude voltage, and frequency of 50 Hz. Every other parameter there is 0. Then you go to simulation. Let me show you what the kind of simulation we are doing. We are doing transient simulation, and the stop time we want to do is transient analysis. The stoppage time is 10 seconds. We want the simulation to run for 10 seconds. Then time to start time to start saving data, I choose 1 second, so that the circuit must have become stable after 1 second. Remember, the frequency is 50 Hz, so which means the period is 0.02 seconds. So at 1 second, the system is stable. So you click on OK. I haven't done that. So you have run this thing. Now you want to simulate the voltage waveform. When you click on this, okay, let me change this thing. I'm coming. Let me check something. Let me check 100. Okay, I think 100 milliseconds. Let's just reduce this thing to, let's reduce the simulation time. Let's use it as let's change it to 100 milliseconds, 100 ms, so that we can get 100 milliseconds. That's a one, let's say 10 milliseconds. 10 milliseconds. Let's simulate this thing again. So we can now see a very visible waveform on the screen. So this is the voltage. Now the current is this. So let me maximize this graph. When you look at this system, you see that due to the presence of the inductor in the circuit, the waveform is not balanced. Even yourself, by physical inspection, you see that the waveform is not balanced. So we want to find the power factor of this system. So how do we find the power factor of this system? I think I've explained that in the previous video, but I'm still going to do it again anyway. To find the power factor of this system, this is the voltage, this is the current waveform, and this is the voltage waveform. So let's find the cursor. This one is tracing the voltage, then this one is cursor what? Is what? Let's give it cursor 1. Let's give it cursor 1. So it's tracing the voltage waveform. So let me assign cursor 2 to this one. Let me assign cursor 2 to this one, so that you can trace the current waveform. This is cursor 1, and this second cursor 2. Okay, this one is tracing the current. Then let this one be tracing the voltage. This one is tracing the current. Then let this one be tracing the voltage. Okay, both of them are tracing. Let this one trace the voltage. This one is tracing the current. Okay, what is going on? Okay, this is tracing the voltage now, and this is tracing the current. Good. So it's just the same way we have been doing it earlier on. One is tracing the voltage and one is tracing the current. Now when you look at the waveform, you see that the voltage is actually leading. You see it at every instant. At this point, the voltage is at the front. At the second point, the voltage is at the front. At the third cycle, the voltage is at the front. Here, the voltage is at the front. So we want to find the phase angle between the voltage and the current. So let's try to make sure that we are putting this in at the very peak. What is the peak of this waveform? We are getting 4.99. I think that will be 4.997. 4.997 is the highest I was able. 4.999 as the highest here. So let me see the highest I'm getting from here. I'm getting 2.4, 2.5. Okay, 2.5. I think 2.5 something is the highest I can get here. 2.5. Okay, let me leave it there. So this is the peak of this, and this is the peak of this. So the cursor difference is 5.2354 milliseconds. So to find the phase angle is just like the same way we have been doing it. The phase angle 360 multiplied by TD over period. So let's bring out our calculator and find the phase angle from this. So phase angle is going to be, so we have our phase time difference will be what? 0.005235. That's milliseconds divided by the frequency 0.02. You get this 0.02, then multiply by 360 degree, you get 94.23. that is our theta. So the phase angle, the angle that separates the two of them, is 94.23 degree. So if you press cosine of 94.23 degree, you see that cos 94.23. Let's find cos. I want to find cos 94.23. Cos 94.23. Cos 94.23. Of course, you see what we are getting. We are getting a power factor that is as low as minus 0.07. Very, in fact, incredibly poor power factor. So which means, you see, the implication of this very poor value is that virtually all the power generated by this system will be wasted in the coil of the inductor. That is just the implication of this simple thing, because we are saying that no power is actually being used by the load. That's why you are getting a value as low, as poor as 0.07. So now that is, you have seen the power factor that is very low. Now let's try to now introduce capacitor in parallel. Now starting in using capacitor to correct power factor, it must be connected in parallel to the what? To the inductor. So let's try to stop the simulation and connect. Let's connect a capacitor. Let me say I want to connect a capacitor of, what's the value I used in my previous analysis? Let me just see the value I used in the previous. Okay, let me say I want to use 50. Let me start by 50 microfarad. Let me connect a capacitor of 50 microfarad in parallel to this guy, and let's see what is going to happen. Don't forget your ground. So don't let us forget our ground. So let me make this one to be 50 microfarad, 50 UF. Use small letter U to represent microfarad. So now let's run the simulation again. Let's find the V, the voltage, and the current. So there's a need for us to find the phase reversal of this guy so that we will be getting accurate value. So when you see what we have here, you will find out that the power factor has improved, because looking at the waveform, you see that they are now more closer to each other. They are more synchronized. They are more synchronized rather than the way it was when the capacitor was not there. But physical expression is not enough. Let's use data. Let's base our conclusion on figure. And what do I mean? Let's measure the way we have been doing it. Let's measure the phase angle now. So click on this here to bring out your cursor. You want to measure the, you click on this guy. You want to measure the phase angle between the voltage. Remember, the voltage is the green, so this one is tracking the green. So let me track the red. This is the green. I want to track let me track the, so this is now the current. So this is the current. You can see the current. What we're having here is 43.3, 43.3. I think if the peak is around 43.396, then the peak of the voltage is around, let's check the peak of the voltage, is 37 point, peak of the voltage, the peak of the voltage, okay, I think the two of them are measuring. This one is, let's one measure voltage and one measure current. So this one is measuring voltage, while this one is measuring, current. Okay, one is measuring voltage and one is measuring current. So we need to be careful not to make a mistake. So okay, so one is measuring voltage and one is measuring current. Good. So we have identified the peak point of the two. So now let's make use of the cursor difference is 2.0044 milliseconds. So as usual, our formula, our usual formula, TD, 360 multiplied by TD over period. So let's see what we're going to get. The cursor difference is 0.002, right? 20044 divided by 0.02, that will give you this, multiplied by 360, that will give you 36.0792. that is the phase angle. Now from angle 90 something degree that we got in the previous, in the first instance, when there was no capacitor inserted in the circuit, we got 97.0, I think 91 point something. Now we got 36. You see that the phase angle has reduced. Now what is cos 36? Cos 36.1 now. Cos 36.1, 36.1 cos. It gave us 0.807. That is approximately 0.81. So which means the introduction of the capacitor, static capacitor, has helped us to correct the power factor from a very poor system to a very good system. You know, if you remember what we discussed in the theory, or what textbook normally teaches, that power factor should be a value between 0 and 1, but 1 is the ideal situation, like this ideal value. 0 should be avoided. Anything close to 0 should be avoided. It's a very poor system. So from this simple explanation, you see that the power factor has been corrected using what? Using static capacitor. Now, worthy of note is the fact that when you are using capacitor, you can have series of capacitors connected in parallel, and in the laboratory we call it capacitor bank. Each of the capacitor bank is connected to a switch in such a way that you can flip the switch to indicate, to actually show, to see the effect of one capacitor before you add another one. If you have gotten the desired value from one capacitor, you stop your correction. But if you are not satisfied, you switch on another capacitor in the capacitor bank array till you get the desired power factor. Okay, so, and we must also note that there is something we call overcompensation and undercompensation. You must not overcompensate your system. If you overcompensate, your system will become overleading. So it has to be very, very minimal. So that is that about that. I hope this video helped. I believe you have learned one or two things in this video, and if you have done that, please kindly click on the notification button, click on the subscribe button to get up-to-date information about our YouTube page, to know when we have new videos. And please refer your friend, refer your course mate, refer your colleagues if you find our videos educating and refreshing. Thank you very much once again. My name still remains Engineer Clemens, Department of Electrical Engineering, Nnamdi Azikiwe University, Awka, Anambra State, Nigeria. Hope to see you guys back in another video. Thank you very much. Bye for now.